Okay, if you remember last time we were talking about methods for searching a tree, and I got this far, didn't get quite through these sort of uninformed searches that I wanted to. So we got as far as depth-first search. The idea of depth-first search is that you, instead of breadth-first, where you implement a FIFO queue, here you implement a last-in, first-out queue. So, for example, we start at node A and then we expand the next level. The first thing that we do is we go down to B, and then in depth first we go over to C, but here we now expand D and E, then we expand D and so on. So the next ones we expand D and E, we go traverse down to D, and then we're going to expand these two nodes. And then finally, having expanded those two nodes, we'll go back up and we'll see that the next one to expand is E, so we'll go down, we'll check I to see if it's a goal, and then we'll need to check E to see if it's a goal. If it's not, then we expand, adding J and K. We'll check J, check K, and then the next we check is C before expanding, and so on. Okay, so I want you to have a think about this. I've only just started lecturing, but I'm already going to get you to think. Is depth first going to be a complete search? So we got some yeses, we got a depends. When I first thought about this, I thought, yeah, it probably is. In fact, no, it's not. And the reason is that if we have an infinite depth space, which we can get, particularly if we have loops involved, then we are not necessarily going to reach a goal. We could end up in an infinite loop situation where we keep expanding and so forth. So we, first of all, we need to modify it to avoid repeated states. Yeah.
I guess implement part of the algorithm that doesn't go into nodes that it's recently been before?
Well, so it depends what you mean by a node, right? So remember in the last lecture we distinguished between nodes and states. And a state is a state of the world, and a node is a representation that you're in a state and you've reached a state via a certain direction and so on. So you actually need to avoid repeated states, not repeated nodes, because the nodes will just keep expanding. There'll be different nodes, but representing the same state. Does that make sense? Anyway, we'll talk about that offline. So the time complexity is terrible if the maximum depth is much larger than the actual depth. And the reason for that is, if we go back to the tree here, suppose the solution were at C, we would have explored all of this part of the tree here down to, well, it could be very, very deep before we actually get to the solution C. So we have to be careful about that. However, if we get lucky, we could be much faster than breadth-first search. The big advantage of a depth-first search is that it's only linear complexity in the size of stuff that you have to keep. Okay? So you only ever have to keep one branch active at a time. Whereas the queue itself doesn't become very large, whereas with breadth-first search, the queue can get exceedingly large. And you have to remember how to backtrack more in your breadth first. Sorry, it's not optimal for the same reason that it's not complete. If you can't guarantee to find a solution, then you can't guarantee to find the best solution. However, it is potentially useful because we can modify it slightly to do something called depth-limited search. And at first sight, this depth-limited search may not seem particularly useful as well, but bear with me until the next slide when I'll show why it's useful. So the idea of a depth-limited search is that you say, I'm going to set an arbitrary cutoff, L, which is as far deep in the tree as I'm going to go. So then we've got a depth-first search, but as soon as we get to a depth L, we'll say, we're not going to go any further. Now, clearly, that's not going to be complete or optimal. We can't guarantee to find the solution because it might live below a particular depth L. But bear with me for a minute. Here's our depth-limited search, and it returns not only one of solution or fail, it will also return something that's not necessarily a failure, just saying, I stopped searching at this point, a cutoff. So, very minor change down here. We just say that we're still doing a recursive depth search here, but if the result is cut off, then we'll return this special case cutoff. Okay? So I'm not going to go through the detail of this algorithm. You can look at it afterwards and see that it's a fairly minor modification from the depth first search. The reason why I introduced that is because we can then use this to create something called iterative deepening search. So iterative deepening search just loops over different depths. So we'll set the depth to 0 and do a depth limited search. Then we'll set the depth to 1 and do a depth limited search. Then we'll set it to 2 and do a depth limited search. So that might seem like a really dumb thing to do at first sight, but in some sense we end up getting the best of breadth first and depth first. Not completely, but so here's what we would do. At level 0, we would expand node A and say we haven't found anything. So that's the end of our search, and it returns cutoff. We then increase L, the cutoff, to 1. And so here are the things that we do. We start at A and we descend to B and we say, well, we haven't found a goal, but we're not going to expand any further because we've reached the depth limit. We'll go back up and we'll expand C. And we haven't found a goal, so we're going to, so at this point we say, well, we reached cutoff. Over here, we reach cutoff at level 1 and we haven't found the goal. So let's increase the depth now to L equals 2. Here are the cases that you go through, the 8 different cases that you go through in this binary tree. We start out here and we expand in a depth first fashion. So we expand down this branch B, expanding D and E, then we go back up to C and expand F and G down here. And each of those, we haven't found the goal, so each of those returns a cutoff. So then we increase to 3. Now we've got these, I guess, well, it should be 16, but I think I've only drawn 12 cases up here. So we search down. You can see in each case we're doing a depth first search. So we search down here, depth-wise, and then come back to here, search down to E, expand there, and so on. And then we're going to search the right-hand side of the tree over here, and so on. So, why is this a sensible thing to do? Well, is it complete? Yes. If there's a solution, we're guaranteed to find it. We might have to keep increasing L, but we're only going to have to increase L to D, the value D, where D is the depth of the solution. We don't necessarily have to go down, in fact, we never have to go down as deep as M, which is the possible depth of the tree. Okay, so we cut off our search at D, and we're guaranteed to find a solution. Here is the order, so it's order B to the D, still not great. All of these searches are not terribly good time complexity, but we get the advantage of the space complexity of depth first search over breadth first search. And if the SEP cost is 1, then yes, it's optimal. We will find the best solution. The reason why it's important, here is a simple numerical comparison. So suppose the branching factor of our tree is 10. I've only shown you binary trees. Let's suppose we had a branching factor of 10 up here, and the depth of the solution is at level 5 of the tree. If we were going to do breadth first search, then at the first level we have to search 10 nodes. At the next level we have to search 100 nodes, at the next level 1,000 nodes, and so on. So we're increasing exponentially. So the sum of all of these things comes to around about 1.1 million nodes we have to search to find that. With iterative deepening search, we search initially 50 nodes, then 400, then 3,000, then 20,000, then 100,000, and by the time we've searched 100,000, we've actually found the solution. So the iterative deepening does better because the other nodes at depth D are not expanded. So for breadth first search, if our solution happened to be at the far right-hand side of the search tree, we would have to expand every node at level D, and which is why we end up with this very large cost. Sorry. This is our breadth first search, not not depth first search. Sorry, there was another point I wanted to bring out about iterative deepening. Yeah. So one of the things you might think about with this iterative deepening search is that surely when we go down a level, we've got to do all of this work again. Notice that each time I go down a level, I'm searching the same nodes again and again and again. Surely that's incredibly wasteful. And yes, it is incredibly wasteful. But I guess the key thing is that in a breadth first search or in an iterative deepening search, the amount of work that you do at this last level completely swamps all the work that you've done at the previous levels. And you can see that in this, in these figures here, that this figure here of 1 million dwarfs all of the other comparisons that we've had to do at the other levels. So that's why, although it's wasteful, it's not a complete disaster, because in fact the search is dominated by the deepest level of the tree that we have to go to, and it's almost in the noise, all the other work that we do to get there. Okay, so here's a summary of those algorithms. You can refer to this later, I won't go through it in detail. And just to emphasize that point, that one of the problems that we might have is that we might have loops in our tree. So if we have a state diagram that looks like this, that we can get from A to B in multiple different ways, or we can have loops and so forth, it can turn what might be a linear search problem into an exponential search problem, because we're having to expand out via these multiple paths via repeated states. Graph search is a search, yes?
Wouldn't breadth first search still be the same complexity at worst case as iterative deepening search? Presuming at the worst case in the iterative deepening search, you have to check every bottom depth, wouldn't that still be the same complexity, big or n, as the breadth first?
I think you're right. I'm going to take that offline, but I think you're right. Yeah. Yes. Yep. Okay, so what graph search does is we keep a list of what's in the fringe, and then we'll check to see whether a particular state is in some closed set, and if it is, then we add the state to closed, just so that we can check to see whether we have considered that state or not already. I'm not going to go into a lot of detail. Here's a bit of a summary that you can use for your reference later. What I really want to do is move on to lecture 4. Okay, so now we're going to talk about informed search. The last lecture was about uninformed search. This is about informed search, and it's building up to an algorithm called A*, which, until relatively recently, was the most famous thing that AI had produced from a theoretical point of view, and one of the most successful and useful algorithms in computer science. So we're going to talk more generically about what we might call best first search, and then we'll narrow that down to this specific instance of best first search called A*. Okay, so here's a review of tree search. In fact, I'm not going to go into detail in this. We've just been talking about tree search. But remember that I guess the key thing in our tree search is this abstract notion of strategy. Okay, so the strategy tells us what is the order in which we pick nodes for expansion. And as you've seen in the last lecture, the order in which you pick nodes for expansion is really crucial for how efficiently you can solve the problem. So the idea in best first search is to use some kind of evaluation function to say, how close am I to the goal if I am at a particular node? And so we'll expand the most desirable node, the most desirable unexpanded node, at any particular moment. So that's this point up here. We're going to expand the most desirable unexpanded node. And in implementation, the fringe is just a queue again, but it's a queue sorted in decreasing order of desirability. So the first thing that we're going to pop off the front of the queue is the thing that we believe at the moment to be most desirable. Of course, if we knew exactly what was most desirable, we would just do it. There would be no sense in searching. We would already know what we need to do. So I'm going to talk about two special cases of this best first search. First one, greedy search. Second one, the famous A* algorithm. So let me take you back to Eastern Europe and this map of Romania. Suppose, in addition to all of this information we have, suppose we've got a ruler and we can put it down on our map, or maybe we've got one of those tables that tells us straight line distance. So that's what we've got over here. This is the straight line distance from each town to Bucharest. Okay? And in fact, some of the numbers don't match up completely. I guess that's because this number here, 85, is the road distance, whereas if I look down here at Uracheni, then it's 80. So the point-to-point distance, as the crow flies, it's 80 kilometres. As we have to drive, it's 85, and so on. So those are the straight line distances. So what greedy search will do is it will set up an evaluation function, which we're going to call h, h of n being the evaluation function at a particular node, will be, in this case, an estimate of the cost from the current node to the destination. So if we happen to be at Uracheni, for instance, then h, we would look up in the table and see that h is 80 kilometres. Or if we happen to be at Efori, we would look up in the table and see that it happens to be 161 kilometres. That's the straight line distance. So in this geographical, this Euclidean world, you can see that that straight line distance is never going to overestimate the actual driving distance to Bucharest. So what greedy search says is we'll have this evaluation function, let's call it HSLD for straight line distance, and greedy search will expand the node that appears to be closest to the goal. So perhaps we start out at Arad here, and we look up the table and see that Arad is, in a straight line, 366 kilometres from Bucharest. So that's what this number here is. There are three possibilities from Arad, and they are Sibiu, Timisoara, and Zerind. And we see, when we expand these three nodes, that Sibiu now has the smallest straight line distance. If we've moved from Arad here to Sibiu, in terms of straight line distance, we are now closer to Bucharest. So maybe that's the better thing to do than expanding Zerind, which is further away, or Timisoara. Now, if we didn't have access to this topology, and we only had access to these numbers, then we wouldn't necessarily know that this is even further away in terms of step lengths as well. Okay, so greedy search is going to pick Sibiu here because it's the smallest number. So we pick it and we get 4 nodes. There are 4 possible ways out of Sibiu, so there are 4 possible actions. And we see that one of them is going back to where we started from. So now the straight line distance has gone back to 366. Unsurprisingly, we're back where we started. Of the other 3, Fagaras is closest at 176 kilometres. So best first search will pick, a greedy best first search will pick Fagaras for expansion. So we expand that and we discover that there are 2 routes out of Fagaras. One takes us back to Sibiu and the other takes us directly to Bucharest. And now we see that the straight line distance is 0, which means we have satisfied the goal. We're now in Bucharest. So, is greedy search complete? And what I want you to do, to think about whether greedy search is complete, is to imagine yourself in Nayant. And now you're a greedy search. What do you do? There's actually only one possibility at this point, and that is to go back to, or to go to Iazi. Now, here's the crux. You're in Iazi, and you're a greedy search algorithm. What are your possibilities?
You take that away.
You can go there to Vaslui, however you say that, or you can go back to Nayant. If you're a greedy search and you're evaluating on which of those two nodes is closer to Bucharest, sorry, we're not going to go to Bucharest, we're going to go to Oradea. Suppose that's our route. We start here, and actually we want to get to here. So our first move, greedy search tells us to get to here, which is probably a sensible thing. But now we're here, what does greedy search tell us to do? It tells us to go back to here. And the reason it tells us to go back to here is that here is closer in a straight line to the thing that we want to get to. Okay? So it's not the most sensible thing to do. Okay, so that's written down there for you. It can get stuck in these loops. So if Oradea is the goal, then we go from ERZ to NAMT, and so on, and we carry on. So we'd need something there to check, would we be going back to a previously visited state? It's still order b to the m, where m is the maximum distance, but it is potentially a big improvement over other search algorithms, depending on how good our heuristic is. It keeps all the nodes in memory, so it's actually very memory inefficient, and it's not guaranteed to find us the best solution. Complete, it will find a solution, not necessarily the optimal solution. It's going to stop as soon as it gets to Bucharest. There's no point in backtracking and saying, oh, actually, it turns out there's a faster way if we actually go further away from Bucharest for our first move, for instance. Okay, so that brings us to the key idea behind A star, this famous algorithm that I've been bigging up for the last hour and a half. In A star, the idea is to avoid expanding paths that are already expensive. So not only are we going to take into account how far we think we are from the goal, but we're also going to take into account how far we've already travelled. Okay, so we'll generalise that evaluation function. We're now going to call it f, and f will be composed of two parts. G is the cost to get to the current node, and h is the expected cost to get to the destination. So h is the same as in greedy search, potentially. It's called h because it's a heuristic. It's something that, providing it doesn't overestimate the distance to the goal, turns out to be a valid heuristic. And g is the actual path. Because we've traversed all these nodes, we know what the cost to get to the current node is. G is the actual cost. So f then becomes an estimate of the total cost of the path through a particular node to the goal. So A star, I've talked about the idea of this heuristic, an admissible heuristic. So hn must be less than or equal to h star, where h star is the true cost to get to the goal. The heuristic must never overestimate the distance to the goal. So straight line distance is okay, because straight line distance is the minimum distance between 2 points. The only possibility for actually travelling is that you go on that straight line or some other path that takes longer. So in that case, the straight line distance would be an admissible heuristic. There is an additional requirement, which is that we want the heuristic always to be greater than or equal to 0, and it needs to be 0 when we're at the goal. That's a sort of fairly obvious criterion. And it turns out that the A star search is optimal, and I'll give you the standard theorem for that in a bit. So how does this work? Let me step you through an example of A star. So we start out at our usual starting place of Arad, and it costs us 0 to get there because we're already there. So this 0 here is G of Arad. 366 is the distance, as we saw before, from Arad to Bucharest. So as soon as we move to any one of these, our cost is going to be the cost of getting from Arad to Sibiu, which in this case is 140, And the evaluation function for A star is that cost, that's G of Sibiu, and 253 is the estimated cost still to go before we get to Bucharest. So the value function for Sibiu is 393. And you can do the same thing for these other two possibilities. The distance from Arad to Timisoara is 116, and the straight line distance from Timisoara to Bucharest is 329. Likewise, from Zerind, the distance from Arad to Zerind, so this is G of n, is 75, and H of n at Zerind, the straight line distance to Bucharest, is 374. And so we get a value for f, the evaluation function, of 449. Okay, so it's pretty clear in this case that if we're going to treat these as expected path cost to the destination, then this one will be the right one to take. The expected path cost is 393, which is better than the others. So we do the same thing, and I'm sorry if you've already got this. I think it's probably worth labouring because it is such an important concept. In Sibiu, or perhaps let me give you 30 seconds just to try and assimilate that, and then I'll have a show of hands to see if anyone doesn't understand why where these numbers come from, or why this would be the next one to expand. Okay, let me flick back. Notice that this number here, 393, is 140 plus 253. The cost of getting to Sibiu is 140. The cost of getting from Sibiu to Fagaras is 140 plus whatever that distance was, and I'm afraid I haven't got the map. I can't bring it up. But if you can hold the map in front of you and the and this chart, you'll see that this number here, for instance, this number here, 220, should be the sum of the distance from Arad to Sibiu and the distance from Sibiu to, was it Reminchu, Reminchu Vilcea. So that's the 220, and 193 is the expected distance still to Bucharest. Would anyone like me to go through that in more detail? Okay, so the next thing we expand is going to be this node, because 413 is less than any of the other values that we've got. Note that it's possible, suppose all of these numbers, in fact that comes out 646, 415 is not bad, but it's possible that all of these numbers are greater than these numbers here, in which case we would expand a node in the other side of the tree. This is because we've now got a sorted queue, so we can expand a node here, and then we can go back and expand a node there. We'll just expand whichever node in the fringe, so here are the 6 nodes in the fringe, whichever one has the least expected cost at the current time of asking. So here's an example of that. We expand from Reminchu Vilcea, and we go to each of these 3 towns, including back to Sibiu, and we see that the expected cost for a path that goes Arad, Sibiu, Reminchu, Vilcea, Craiova is 526. This one 417, and this one 553. So the next node to expand is in fact Fagaras, because its expected cost is 415. So that's the next one that we expand. Once we've expanded that, we see that the expected costs are 591 and 450. So we come back here where the expected cost is 417. And then finally, we can expand these three, and we see that the expected, h of n is now 0, and so the total path cost was 418. Okay, so that's an example of running A star. Yeah.
How would A star work in that infinite loop example you gave for greedy search?
So what's going to happen if we go back to here? So suppose we start here and we move to ERZ. So that seems like a good move, and that's in fact the move that A star would make in that first instance. Now A star says, what can I expand? Well, I can expand to Nahant, or I can expand to Vaslui. Where greedy search will simply look at how far away is Nahant from Oradea and say, well, that's the thing I should choose. In A star, it will look at how far away am I and how far have I travelled. So it's going to be 87 times 2 plus that distance. Whereas this distance here will be 87, it will be, if I started here, it will be 87 plus 92 plus that distance there. It may still take us back to Nahant, but as we keep moving backwards and forwards, that cost is going to accumulate, because we're accumulating that path cost. So eventually, the distance of 87 plus 92 plus that distance will be less than the fact that we've moved backwards and forwards from there to there, and it will say, much better to expand this one. And yeah, okay. Okay, so this is a standard proof of optimality of A star. So the usual thing is that you would say, let's suppose that there is some node that is optimal. A suboptimal goal G2 has been generated and is in the queue. Okay, so we've reached the goal, but it's not optimal. And if we stopped at that point, then, or if we'd managed to reach that and stop, then that would prove that that A star was not optimal. So we'll assume that we're in that state, and now we're going to show that that's a contradiction. We can't possibly be in that state. So let's suppose we're at G2 and it's in the queue. Let's suppose that there is some unexpanded node that is on a shorter path to the true optimum G1. So it's labelled G here, but G1 up here. So let's suppose that there is an N on the true path, on the path to the true goal. So first of all, we know that if we're at this suboptimal goal, because it's a goal, we know that the expected cost is 0. So that means, remember that F is the sum of the expected cost plus the actual cost to get there. So the value function at G2 must be equal to the path cost to get to G2. That's what this is saying. This is the expected cost to G2 is exactly equal to the path cost, because we're already there at a goal. If G2 is suboptimal, which it is by assumption, then it must have a bigger path cost than the cost to get to G1. Okay, so that means that the value function at G2 is greater than the path cost to G1. But if the path cost, but F must be greater than G by construction. We created F as being the sum of G and H and said that H has to be greater than or equal to 0. And H is admissible, and therefore this G must be greater than F. So what we've found is that so this is F of n, sorry. So it's not just that we're at the goal, but the cost from n to G must be greater than or equal to h of n. H is our heuristic. How our estimate of how far we are from n to g. And so g plus, so f of n is going to be given by g of n plus h of n, and g of g1 plus the total path cost to g1 must be greater than our estimate of the cost to g1 through f. Sorry, that's the right words. H is admissible. We can never overestimate the total path cost. So that says that the actual cost to get to the goal must be greater than the estimated cost to get to the goal through node n. So what that means is that the f cost, the value function at n, is less than the value function at g2. But if that's the case, we would never have selected g2 in the first place, because A star tells us that we have to pick the one that has the lowest value function. So we should have picked n, not g2. So that says that we are going to descend to the optimum goal fastest. Yeah?
The bit that I don't get is HG2 equals 0. That still doesn't quite make sense to me. Why that has to be 0.
So if you're at the goal, then the estimate of the cost to get to the goal has to be 0. G2, by assumption, is a goal. We've reached the goal, but it's a suboptimal goal.
Yeah,
Okay?
Yeah, I thought it was on the path to a suboptimal goal.
Yeah.
No,
Yeah, so there may be multiple things that satisfy our goal state, and we're interested in the best path to get to that goal state. Okay? Okay, so is A star complete? Yes, unless there are infinitely many nodes with f less than fg. It's still exponential, but it's a much better exponential than before. It's still complex in terms of the amount that it keeps in memory, but yes, it's optimal. Okay, so A star is going to expand all nodes for which, so what have I got here? C star is the optimal cost, the cost associated with the optimal path. So it's going to expand all nodes for which the value function is less than that optimal cost. It's going to expand some nodes for which the f of n is equal to the optimal cost, and it's never going to expand a node for which the value function is greater than the actual cost to the goal. Okay, so I wanted to talk a little bit about heuristics and consistency of heuristics. So heuristic is consistent if so h of n is our heuristic, and it must be less than or equal to the heuristic cost of a predecessor node plus the cost of getting from that predecessor node to the current node via some action, via some path. So that's just this triangle inequality here that you're used to when you're dealing with metric distances, but it can be expanded here in the context of our heuristic. Essentially what we're saying is that the estimate to get from n to our goal here, h of n, must be less than or equal to the cost of moving from current node to a new node plus the estimate from that new node to the goal. And if h is consistent like that, then what we have is that f of n prime is g of n prime plus h of n prime. That's just by definition. Now if we substitute in for hn prime up here, hn prime is just the cost of moving from n to n prime via an action A plus the, g of n prime is equal to g of n plus the cost of moving from n prime to n via action A. and we still have this estimated cost in here. And that must be this term here. We've just said that h of n is less than or equal to the sum of those two things. So if h of n is less than the sum of those two things, then this whole term here is greater than or equal to this whole term here, and that, g of n plus h of n, is by definition the value function at node n. So what this is saying is that f of n, this is our value function, is non-decreasing along any path. Okay, so final few minutes. Really important to talk about admissible heuristics. So let me give you some examples. The example so far has been a geographical one. So we've thought about straight line distance as being an admissible heuristic. And it's easy to see that that satisfies the triangle inequality. Suppose we've got an 8 puzzle. Here are a couple of possible heuristics. One might be this h1n is just the number of misplaced tiles. Okay, so you should be able to see that if you count the number of misplaced tiles, the total number of moves to get to the solution has got to be more than that. It's lower bounded by the total number of misplaced tiles. Maybe a slightly better heuristic is the total Manhattan distance. So that's not just is a tile in the wrong place, it's how far as we move the tile along up or down, left, right. So Manhattan distance of this square 6 to the top left square 7 is 1, 2, 3, okay? So Manhattan distance is moving along north, south, east, west directions. Maybe we could call it Adelaide distance because Adelaide's on a grid like that as well. So our start state here and our goal state here, have a think about what the values of those two things are. 1 minute. What is h of s1 for this start state here? And what is, sorry, h1 of s, and what is h2 of s?
When you say total Manhattan distance, are you talking about like the addition of all Manhattan distances?
Exactly, exactly. Each misplaced tile, if a tile is not misplaced, its Manhattan distance is 0, and the total Manhattan distance is the sum of all of the distances of the misplaced tiles. Okay, someone wearing a hat. What's your answer to h1 of s? I can see 2 people wearing hats. What's your answer? Do you know how to work it out? Other person wearing a hat. Yep, why is it 6? Absolutely. So let me repeat that in case you didn't hear it. Tile 2 and tile 6 are in their correct locations. Every other tile is in the wrong location. So there are 6 tiles that are misplaced. h1 is equal to 6. Okay. Someone with blonde hair. What's h2 of s? Anyone managed to work that out? Actually, there aren't many blondes in this room, are there? We've got 1, 2, 3, 4. Almost as few blondes as there are hats. Anyone else want to volunteer an answer? 0? No? 14.
Is it 14?
I haven't worked it out myself, but let's have a look. Yes, it's 14. Okay? So, the sum here is the sum of the distances of each tile from its location. So, 7 should be down here. So actually, I don't know why I've got 4 there. Okay, yep. So 1 should be up here. So 1, 2, 3, 4. 2 is in its correct location. 3 should be up here. So it's 1, 2, 3. So we get a 3. 4. It should be down here, so it's 1, 2, 3 away. 5 should be here, so it's 1 away. 6 is in its correct location. 7 should be down here, so it's 2 away, and 8 should be here, so it's 1 away. Add those up, you get 14. Okay? Okay, I think this is the last thing that I want to go through in this slide. So the idea of dominance between different heuristics. So if a particular heuristic, H2, is greater than or equal to H1 for all possible nodes, let's assume that they're both admissible, then we say that H2 dominates H1 and it's better for search. In effect, what we're saying is that H2 is a better approximation to the true distance. Remember that all admissible heuristics have to be less than the true value. So one that's bigger is getting closer and closer to the true value. Okay, so here's an example of the difference between different kinds of search. So for iterative deepening search for some random problem, we would have to search over 3 million nodes. For heuristic number 1, I think this is probably for the, no, it's just a generic search with depth equal to 14. Heuristic 1, we might search 539 nodes. For heuristic 2, we might search 113 nodes. So you can see that there are very significant gains to be had, firstly with using A star, and then with using a decent heuristic. And one other thing to note is that if we've got 2 heuristics, one dominates the other, but they're both admissible, then we can create a new heuristic. In fact, given any admissible heuristic, one doesn't have to dominate the other, HA and HB, then we can pick the maximum of the 2 in any circumstance and generate a new heuristic, H max n. And it's guaranteed to dominate both HA and HB. Okay, so, and this is the final thing. How do you go about generating a useful heuristic? So how do we think up the idea that maybe moving the tiles around would be a good thing? Well, quite often a good way of thinking about this, a good way of thinking of an admissible heuristic, is to think about the exact solution to a relaxed problem. Instead of thinking about the heuristic as being an approximate solution to the actual problem, think about the heuristic as being an exact solution to a relaxed version of the problem. So let me explain what I mean by that. Think about the 8 puzzle. So if we relax the rules of the 8 puzzle so it can move anywhere, then H1 gives us the shortest solution. If we relax the rules so that a tile can move to any adjacent square, then the Manhattan distance is an exact estimate of how far. If we were able to do that, obviously in the real 8 problem you can't. But so the key point is that the optimal solution cost of a relaxed problem is never greater than the optimal solution cost of the real problem. So think about the geography as well. If we relax the problem to say that we can travel in a straight line distance from A to B, then that generates a heuristic for the actual problem where we have to travel on real roads. Okay, I'll finish this off on Monday. There's only 1 or 2 more slides, but I better finish there. Yeah, it is, right. So